Hey, Katie.
Hi, Ben.
What are we talking about today?
We are talking about heterogeneous treatment effects and how you can use machine learning methods like decision trees to understand causal inference questions like who is going to respond to a certain treatment.
Awesome. You are listening to Linear Digressions. So, causal inference is saying we did a certain thing and it caused this other thing to happen.
Yeah, let's take the example of trying to understand, do medications development. So you're trying to understand there's a bunch of people who are, let's say, they're very sick. Maybe they have, let's use cancer as an example. So a whole bunch of cancer patients were interested in trying to think of new medications that might improve their prognosis. And we are in the business of trying to unpack that problem, like medical researchers or something working in clinical trials. So if we were to naively take, let's say, like everyone who has cancer and give them our new medication, then over the entire population, we would calculate some kind of what we would call the average treatment effect. So that's of all of the people that we treated, how many got better, how many, stayed the same or got worse. And then you can average that out for the entire population. You say on average, people get 10% better. Or they get 20% better or something.
Is this example including, say, a control group? Or is this just looking at the effect over time when you give a certain treatment to a group of people?
Yeah, let's suppose that we have done our proper, control arm.
Okay.
It's randomized, all that kind of stuff. So
Got it.
We can say that, any average treatment effect, it's a true treatment effect. It's not, an artifact of confounders.
Okay.
Yeah.
So you've got a bunch of people, you give them experimental medication, and then you can determine how much better or worse that group did as a whole.
Yeah. So let's use that scenario. So that's what we would call the average treatment effect. Or if you want to be even more precise, the average treatment effect on the treated. Because, for reasons of causal inference. But anyway, average treatment effect is saying just if you were to pull some person at random from the population. But if you were to dig into the data a little bit more, in the case of the reason I picked cancer is because that's a disease that's got a lot of genomic drivers of the disease as a whole.
So that means some people will respond better and some people will respond worse based on something about them, like genetic markers or something.
Yeah, so the treatment that you're giving them might be targeting a particular pathway or mechanism of action, some particular process in the cells themselves. And if that's a process that's driving the cancer overall, then targeting it with a therapeutic, if you have that particular mutation and you take that particular therapeutic, you might have be very, very responsive to the treatment. You might have a much, much better outcome. Whereas if there's, your neighbor in the next bed over might have a totally different type of genomic driver of their disease. So you can give them the same medication and they might not respond to it at all because it's just not targeting the thing that's actually driving their disease, right? So
interesting.
Yeah. So the average treatment effect would take those two patients and kind of pool them together and say, well, overall, maybe they got, on average, people get a little bit better, but maybe not way better. But if you were to split it into subgroups, say based on a particular genetic mutation, if you were to find the right way to split the data, then you might find that there's a subgroup that's a very strong responder for some reason. And there's other subgroups that might be much weaker responders. And if you're doing a data analysis, of course, or if you're a scientist studying this disease, then that heterogeneity of the treatment effects is something that's very, very interesting to you because it gives you more information about how the treatment is actually working. It might help you understand who you should be, which types of patients would be good candidates for this treatment, all that kind of really important stuff about the problem that you're trying to solve.
How do you decide how to split the group? Because that seems like a difficult question to answer.
Yeah, great question. So there are a few answers. One is you can use domain knowledge, maybe something about the way that this treatment is supposed to work, and you can you have the resources to like test all of those patients. Maybe you
make a hypothesis and
yeah. But you can imagine that, you might have a lot of different hypotheses and you want to be able to say split your group based on any or all of them. And, maybe there's even a way of splitting your data on the basis of something that you haven't even thought of before. Like maybe you guess wrong about what's driving the response to that treatment. And if you were to just pick the wrong way to subgroup the data, then you could miss it. So in general, the question of how to find the subgroups, there's a couple of different approaches. So one is you can try all of the subgroups. So you can have a very finely grained division of your data into like many very small subgroups. The problem with that is that just based on statistics, there's a really good chance that some fraction of those subgroups, like let's say 5% of those subgroups, if you pick a p-value of 0.05, will look like they have some kind of statistically significant, deviation from the null hypothesis. And you're saying like, haha, we found a group of super responders, but it's like, you just like, that's just luck of the draw.
I was wondering about that. Yeah, because if you take any data set, no matter how big, and then you just keep testing different ideas, eventually you're going to get the data that you want, but not because that's actually, representative of what's really going on.
Yeah, you just keep picking up little shoots of hay, and then you're like, is this a needle? Is this a needle? Is this a needle? And like, because of the way statistics works, like some percentage of the time you'll be like, haha, yes. And then you've had a spurious discovery. And you have to worry about that.
It kind of seems like shaking a magic 8-ball over and over and over again.
Right, until it tells you like the thing.
And it's like, no, the answer to your question is no. But eventually.
Yeah, if you shake it enough times. So we have kind of the statistical equivalent of that if you're trying to do like a comprehensive search across subgroups. Nonetheless, there's ways that you can correct for multiple hypothesis testing is what this is called. But instead, what I want to focus on today is another idea for a way that we could find the subgroups. And this is from a method by Susan Athey and Guido Imbens, they have kind of an interesting background that I want to digress into here for a moment, which is that they're econometricians. So these are folks who have a background in studying causal inference, and they think a lot about computing treatment effects and all of this kind of stuff. But they have a lot of expertise in machine learning as well, which econometrics and machine learning haven't always been super closely entwined. But these folks sit at this interesting intersection of the two. And so the paper that, or the method, this is from a paper from 2016. It's entitled Recursive Partitioning for Heterogeneous Causal Effects. So recursive partitioning, what they're actually talking about here is basically a decision tree. So if you're a machine learning person, like probably most of our listeners are, you're familiar with the idea of a decision tree, which is namely this binary tree structure that allows you to split the data into, according to the binary decision rules of a tree, split your data into a bunch of different little partitions. Each of the leaves can be thought of as a partitioning of the data. And then in a decision tree, what you're usually trying to do is for each of those leaves make a prediction about some kind of class label for like a supervised learning problem. But in this case, what they're thinking about is, well, let's think about each of those partitionings of the data is actually like a subgroup in our analysis. And we want to be calculating the treatment effect in that subgroup. And the decision tree itself actually gives us like the structure of the subgroups that we want to be analyzing the data in to look for different effects according to the subgroup or the subpopulation that someone falls into.
Okay, I think that makes sense, but it still seems like we're searching for a needle in a haystack over and over and over and over and over again, and eventually we'll find that needle accidentally. So like, how do you ensure that you're not doing that if you're testing a whole bunch of different circumstances?
Right, because the way that you're training that decision tree in this case is you're looking for different subgroups that split your population according to how they respond to the treatment. So, you have kind of an infinite number of different cuts that the decision tree could make in order to partition the data set, which means that it can pick the cuts that shove all of the super responders into one group together, and then it's easy to think that you've, it's easy to overestimate, for example, the treatment effect that you have in that group.
Is that what we refer to as overfitting?
So, kind of. So, overfitting in the case of like a supervised classifier usually means, I think of it as like the classifier has memorized the data, and so it's not going to generalize well to new cases. I think in this case, it's a similar idea, but it's a little bit different. It's a little bit more that if you were to use the same data to create the tree and also to estimate the causal effect in each of those subgroups, you will overestimate generally the extremity of the effect, because the algorithm is trying to put cases that look similar like all together. Whereas if you were to have a second independent data set, then it would be a little bit less likely to have like statistical fluctuations like kind of clumped together in exactly the same way. So you would probably get treatment effects that are like a little bit different and that are truer to the actual like real world God's eye view causal treatment effects.
So is that the answer then? Go and collect more data?
Kind of, but not exactly. So the other innovation in this paper, besides the idea that we can use a decision tree structure to, partition our data set into all these subgroups, is the cost of that is that we have to actually hold out half of our data and use that to estimate the size of the causal effects in each of those subgroups. We can't use the same data set to both create the partitioning and to measure what's going on in each of the subgroups. Instead, we need to pay the price of holding back half of our data and sending it through the tree after we've created it to estimate what the effect size is in each of those leaves. Otherwise, that's the only way to get an unbiased estimate of the treatment, the size of the treatment effects in each of the groups.
That makes sense. I guess because you can't really go in the real world and just collect more data that's biased and that's unbiased, I guess. But interesting that you have to...
if you had a lot more time, I guess like splitting the data set in half and then training on one half and estimating on the second half is like kind of like collecting more data in a sense. But yeah, the general idea though is that you have to have separate data sets. So it's probably easiest just to use one data set to begin with and split it into pieces. Because then you can do other things like fit the data or fit the tree on each of the two different data sets and like see if the tree is totally different for the two data sets.
Interesting.
Or,
to see if you split the data set in half in a good way or in a biased way.
Yeah, and this is like going a little bit beyond the scope, at least of this paper, I think. This is me like freewheeling a little bit here. But what they do spend a lot of time talking about in this paper is from an econometric perspective, like how do we construct an unbiased estimator using this biased machine learning approach. And yeah, the answer is they call it like an honest method of estimating the effect size, which basically means you have to put half of your data set into a black box and not look at it until you're done, which is, it's kind of an expensive choice to make, is to, forego the precision that you get from incorporating that data. But in terms of it enabling you to both use this machine learning method and also to get unbiased estimates out of it in the end, maybe it's worth it. So that is that for causal trees. So we'll have a link to the paper on lineardigressions.com for those of you who are into that. But yeah, it's a really interesting intersection of kind of two areas that we like to talk about a lot, but that don't always intersect, namely the machine learning world and kind of the causal inference, econometrics or inferential world, or like whatever. So if you are also interested in seeing these two worlds come together, you should check it out.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi.
find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.